Hello, welcome to this lecture module on optics. I am M.R. Shenoy from the Department of Physics at IIT Delhi. In the following lectures, we will discuss about optics, which deals with the science and technology involving light propagation. The level of discussion will be at an introductory level compatible with the higher secondary school, and we will try to emphasize more on the basic concepts, and I will also try to work out some examples, try to show some demonstrations in the course of the lectures. So, optics. In this first lecture, we will give a general introduction. I will try to cover the scope of the course and give you a general idea which should motivate about the importance of optics, the limitations of various approaches in optics, and the various applications. Optics deals with the science and technology involving the propagation of light. The range of phenomena or effects and practical applications are very wide, from most common applications like spectacles for correction of vision. Many of us wear spectacles, including large number of students, for vision correction, and to modern high speed optical fiber communication for transmission of multi gigabits of information and data. Optics plays an important role. From natural phenomena such as formation of rainbows, which I will discuss in one of the classes in the one of the subsequent lectures. From natural phenomena such as formation of rainbows to the most recent discovery of gravitation waves, the detection of gravitation waves, which involves optics, and optics plays a very important role. There are three different approaches in the study of optics. Usually there are three different approaches which are followed, and they are the ray optics approach, wave optics approach, and quantum optics approach. Sometimes people talk of intermediate other approaches like beam optics and electromagnetic optics and so on, but broadly there are three approaches, namely ray optics approach, wave optics approach, and quantum optics approach to study optics, optical phenomena, effects, and applications. Why is it necessary to follow different approaches? We will try to answer this as we discuss further. Let me start first with ray optics. In ray optics, propagation of light is represented by rays. So, what is a ray? A ray is a light path along which the optical energy flows. The direction of energy flow is indicated by the arrow sign. Typically, we show, for example, this is a ray path. The arrow indicates the direction of flow of energy. Optics deals with light, a form of light is a form of energy, and the arrow indicates the direction of flow of energy. In a homogeneous medium, that is a medium of uniform refractive index, normally when we say a homogeneous medium, it means that the properties of the medium are the same everywhere at every spatial point, every location in the medium, the properties of the medium are the same, and then we say that it is a homogeneous medium. So, in this case a medium of uniform refractive index, then ray paths are straight line. Ray paths are straight lines as shown here. So, obviously, if I have underlined this, that ray paths are straight lines, the question arises, does this mean that there are curved ray paths? The answer is yes. We will discuss this in more detail as we go in subsequent lectures. If the medium, for example, if the medium, so let me draw a medium here. So, this is a medium. If the refractive index at different points in this medium are different, for example, we may have a graded index medium, a graded index medium, graded index medium. For example, in this medium, the refractive index may be maximum here in the center and goes on decreasing on both the sides. That is, if I plot here the refractive index variation, so along this line, if I plot n, and let us say this is the x direction and I am plotting n of x, then refractive index is graded. Let us say it is continuously dropping like this. In fact, this is one of the practical cases which we will try to discuss at a later point of time, but if the refractive index varies in a particular direction, it is called a graded index medium. It is not a uniform index medium, it is a graded index medium. In such cases, ray paths can be curved. For example, a particular ray path may be like this. A ray may travel in this fashion, may not be a straight line, it may be a curved path in a graded index medium. The more discussions are not really in the purview of this course, but we must know that ray paths are straight lines only in a uniform medium, that is a medium with uniform refractive index. Now, the propagation of a beam of light in ray optics, the propagation of a beam of light can be represented by propagation of a bunch of rays. A beam of light can be treated as a bunch of rays. For example, if you take light from a battery torch, a battery torch like this, we know that the light which is coming out from a battery torch. So, I do not know whether you can see this or not, but if I show this battery torch here, the beam of light which is coming from a battery torch. So, let us say this is, so light beam is coming, then the output beam can be represented in terms of a bunch of rays. The beam is of course diverging, the output beam can be represented in terms of a bunch of rays, rays travelling in different directions because the beam is diverging as it travels. So, it is like this. So, the torch is here and if I switch on, the beam travels in the forward direction, but it is spreading as it travels. Similarly, if we take for example, a laser, if I take a laser, we know that laser beams are highly collimated, highly directional, still it can be represented by rays, parallel rays. There is a finite divergence even in the laser beam, but in general they are highly collimated and therefore, the divergence is very small, the spreading is very small. So, we can represent it by rays. If we consider the sun, for example, we see this in various photographs or pictures, that sun. So, here is the sun, then sun rays coming out in all directions. So, sun rays are shown like this. in the ray picture. So, in the ray picture different sources. So, this is a laser, it is a torchlight, a battery torchlight or a sun ray. In fact, I think I have a diagram which shows this very clearly. So, bunch of rays from different sources, a torchlight, a laser beam and a sunlight. I have taken 3 typical sources and I will look at the representation of a beam of light coming out when it is ray optics approach, when we have wave optics approach and when we have quantum optics approach. So, let us see further. We can also trace rays through a medium. For example, tracing rays through a medium. How can we trace rays through a medium? A simple experiment which we had done many years before when I was a school student, that we had an experiment where we had a glass block and we need to trace rays through this medium. So, what is done is the experiment is quite simple. So, you first draw a line around this glass block, keep the glass block and draw its margins, its periphery. So, this is the periphery drawn by pencil. Then keep the glass block, draw a line which represents an incoming ray, keep 2 awl pins here, that is on a drawing board we clip 2 pins and then observe the image of these 2 pins from this side. So, what would happen is that the ray, if this were a ray, it enters from a rarer medium to a denser medium. So, this is glass. So, this is glass, refractive index let us say 1.5 and outside we have, we will discuss this in more detail later, but the ray will start bending towards the normal. So, it will bend and it will come here. Of course, we cannot see this. So, the ray bends here. At this interface it will bend again away from the normal, So, if you are observing from here, that is if we observe, this is the human eye. So, this is the human eye. So, if we are observing from this end here, the block is kept here, we are observing from here, then we align ourselves such that the 2 awl pins are along the same line and appear as one pin, one post like this, and in that direction we place the 3rd pin here. We take one more pin and place the 4th pin. This ray is not there, this ray is right now it is not there. So, I place the 4th pin here, so that all 4 pins are aligned, that is the 2 pin and the images of these 2 pin are aligned and look like one. Then connect these 2 points, remove the pins and connect the points. So, join a line. So, this is a ray. First we draw a ray path, a straight line, place 2 pins here, that is pin 2 pins like this vertically, and then keep the block, observe from here and place a pin in a position such that it masks or it all the 3 pins, that is the pin placed and its images look like one single pin. Place the 4th pin such that all 4 pins are aligned, the 2 pins and the images of these 2 are aligned, and then take out the pins and join this line here. The point of intersect, now we have the point of intersects, let us say this is P and this is Q, and join this with a straight line. This is a glass block, a uniform medium, and what we have achieved is tracing ray path through the medium. Now, how do you know that this is correct? This is correct because we also verify the Snell's law, the Snell's law. So, if we measure this angle here, we measure the angle here, we also measure the angle here and we measure the angle here. So, this is the angle of incidence, and so this we will discuss in more detail at a later time. This here is the angle of refraction or this is the angle of incidence, and we verify the Snell's law. Snell's law. We will discuss this at a later time, Snell's law, which says that sin I by sin r is equal to n2 by n1. So, this is n1 and this is n2. So, this is Snell's law, and what we do is we trace the rays, measure the angle I here, measure the angle r here and verify whether this relation is satisfied. Indeed, we find that the relation gets satisfied within the limits of course experimental error. In fact, Snell's law is determined empirically using a similar phenomena, using a similar method of tracing rays through the medium. However, Snell's law comes out analytically, automatically in the case of wave optics. So, in wave optics, Snell's law comes out analytically. It is not an empirical or a proposition. Snell's law comes out analytically. Because in wave optics we treat light as an electromagnetic wave. It has to satisfy certain boundary conditions, and when we apply the boundary conditions, the Snell's law comes out automatically and analytically in the case of. So, that brings us to the next approach. So, what I have briefly described is what is ray optics, and we will discuss more about ray optics in the subsequent lectures. So, that brings us to wave optics. In wave optics, a beam of light comprises of large number of propagating waves. A beam of light is represented, is the same torchlight. Now, I have represented it by a large number of waves which are travelling, emanating from the torchlight. So, this is the same beam. Earlier we represented these as rays, now we are representing these as waves. What type of waves are these? These are electromagnetic waves, So, those of you who have studied the chapter on electromagnetic waves, you may be familiar with it, but if you do not know, I will briefly show what is an electromagnetic wave. So, an electromagnetic wave, so here is an illustration of an electromagnetic wave. A wave which is propagating in the z direction has electric and magnetic fields varying. The electric field varies sinusoidally. For example, in the x direction, electric field is varying, oscillating sinusoidally. So, what is shown is the arrow is the electric field is a vector. So, with the time or with the position, the electric field is oscillating sinusoidally and the magnetic field is perpendicular to it. So, the electric field in this case, in this diagram, the electric field is in the x z plane, it is oscillating in the x z plane, whereas the magnetic field is oscillating in the y z plane, that is in the horizontal plane here, y z plane. So, it is perpendicular to each other. At every point the electric field and magnetic field are perpendicular to each other. This representation of electromagnetic field clearly tells you that it is a propagating wave with sinusoidal oscillations of the electric and magnetic field. So, the electric field, if you take the electric field for example, it can be represented it is in the x direction. So, I have written x cap, which is a unit vector in the x direction, amplitude A of a certain amplitude A maximum displacement, maximum strength here of the electric field is A, and sin omega t minus k z. Omega is the angular frequency, which can be written as 2 pi into f. Omega is 2 pi f, f is the frequency into time, minus k, k is the propagation constant, which is given by 2 pi by lambda, where lambda is the wavelength of the oscillations. So, 2 pi by lambda into z. So, if we take out k, for example, this 2 pi by lambda, if we take out, we will get here f into lambda, which is nothing but the velocity, frequency into wavelength is velocity. So, we can also write in the case of a light propagating in the medium in free space, this v is nothing but c, the velocity of light. So, x cap a sin k v t minus z. We can write this in different forms. So, you can write the electromagnetic wave in different forms, but the important point to see is it has an amplitude, a certain velocity and a frequency wavelength, amplitude, like typical of any wave. So, light is an electromagnetic wave, and in wave optics we deal with the electromagnetic waves. So, if I were to represent the same three sources, namely the torch light, the laser and the sun, how would I represent? So, here it is. So, I could represent it as, here is the torch light waves emanating from different sources. Earlier I represented it as straight lines coming out, rays coming out. Now, we represent it by waves, a bunch of waves, a bundle of waves which are coming out of the torch. If you see more carefully, I have drawn it in such a way that the laser light here, the waves are coherent, they are coherent waves. Coherent waves, we will discuss about this when we come to wave optics, we will discuss about coherent waves and incoherent waves in more detail, but at the moment coherent waves here represent if the two waves which are shown here, typically it is not just two waves, but I have shown two waves which are in phase everywhere, or if there is a constant phase difference between the component waves, then we say that they are coherent waves. In contrast, what I have shown here are incoherent waves, because there is no phase relationship between the between the component sinusoidal waves which are coming out of this. This makes a lot of difference when we discuss interference in wave optics, and I have illustrated here how would we represent the sun. So, that is wave optics. In quantum optics, propagation of light. So, this is the third approach, this is the most advanced approach. Quantum optics is an advanced approach which is used or which is applicable, which is practical in certain circumstances which I will discuss. So, in quantum optics, propagation of light is described in terms of propagation of large number of tiny particle like, it is particle like, it is not particles. So, tiny particle like packets of optical energy, packets of optical energy called photons. So, in quantum optics, propagation of light is described in terms of propagation of large number of tiny particle like packets of optical energy called photons, which travel with the speed of light. The energy of a photon corresponding to light of a particular color or wavelength lambda is given by E is equal to h c by lambda, which is equal to h nu, nu or f. Nu is the frequency or f is the frequency, you can write h f or h nu. H is called the Planck's constant, this is named after the scientist Max Planck. H is the Planck's constant. So, E is equal to h nu. is the energy of a photon. Now, before I proceed further, if I were to represent the same source, torch, laser and sun in the quantum optics picture, how would I represent? It is just a schematic. So, I would represent it as a bunch of photons emanating from different sources. Is the torch light? So, bunch of photons, the number are extremely large. We will come to this, the bunch of photons emanating from the torch light. Laser, again the bunch of photons, but highly collimated, almost aligned along a line, and bunch of photons coming out of the sun. The number really, this is just a schematic illustration, but the number of photons which are coming out are extremely large, and really I cannot show it as discrete points, because the number is so large that it would look all pervasive everywhere. It would look the whole region outside would look uniform with the photon energy or photon packets. Now, what is the energy of a photon? The energy of a photon corresponding to visible light. Let us get some idea what is the energy of this packet, the photon. So, energy of a photon is given by hc by lambda. H is the Planck's constant, its value is 6.6 into 10 power minus 34 joule second. C is the velocity of light, speed of light, 3 into 10 power 8 meters per second. Lambda, if I consider for example say yellow light, so let me say lambda is about 600 nanometers, just to estimate what is the kind of energy that we have for a photon of yellow light. So, you substitute here and what we get is E is equal to 3.3. So, 6 goes 1.1 times multiplied by 3. So, 3.3 into 10 to the power of minus 19 joules. That is an extremely small energy, 10 to the power of minus 19 joules. What does this mean? This kind of energy, what does it tell us? It tells us if there are 10 power 19 photons were to be incident on a screen or a photodetector in 1 second, it would correspond to a power of 3.3 watts. What is this? So, I have energy E is equal to energy of one photon is 3.3 into 10 power minus 19 joules. If 10 power, this is the energy, if there were 10 power 19 photons incident per second, that is second inverse, then we have this is equal to 3.3 into joule second inverse. Joule second inverse is joule per second is watt. So, this is nothing but watt. So, that is how I have written 3.3 watt. So, what is this? This is the power, energy per second is the power. So, the power is about 3.3 watts. When 10 to the power of 19 photons are incident per second on a photodetector, let us say, or on a screen, then the power is approximately 3.3 watt. This is the kind of power that we handle in practice. In practice, we have bulbs which are of 40 watt, 60 watt, a tube light which is of 40 watt, an LED lamp which is of 5 watt or 10 watt. So, typically we handle light sources which are of the order of watts. So, what does this mean? If an LED is of 5 watt, it means it is giving of the this is 3.3 watt. I have just calculated 3.3 watt with 10 to the power of 19 photons incident per second. So, an LED of 5 watt or 3.3 watt to be precise would give 10 to the power of 9, would emit 10 to the power of 19 photons per second. the number of photons involved in the common power levels which we handle every day are extremely large, and therefore, if we the numbers are so large that it is beyond comprehension or beyond measurable limits. This is the kind of numbers which you cannot measure, but if the intensity were to be very low, if the power were to be very low, for example, at extremely low powers, let us say at extremely low powers 10 to the power of minus 15 watt or less, the number of photons involved are in thousands, and it is possible to count the number of photons incident on a photodetector. At very low powers, it is possible to count the number of photons incident on a detector, and in fact, there are commercial equipments, commercial devices which are available, which are called photon counters. One can buy these photon counters. So, these can count the number of photons incident per second when the power levels are extremely small. If we push this a little forward, if you reduce the power further, then it is possible the power is so small that the photons come almost one at a time. The photons come out of the source one at a time. So, these are called single photon sources. They are not coming at a regular period. The output photons follow certain distributions and statistics, and of course, with applications, single photon source. This is the current advance in quantum optics with the applications. This is beyond the scope of our course of lectures here. So, we will stop this discussion about quantum optics here, but the discussion with these three, what do they bring out? They bring out that quantum optics becomes extremely important, and you can see the quantum nature of light, that is, you can count photons coming out of a source when the power levels involved are very small and the precision of measurement required is extremely small. For example, let me give you an idea that when do we use calculator? For example, to multiply 2 and 4, 2 into 4 is 8, we do not need a calculator. But suppose I have to multiply 2.38746 by another number, say 4.00246. And I am expecting an answer with a precision of 6 decimals, then I cannot do it. I have to use a calculator. When I need such level of precision, I need a calculator to get up to 6 decimals. So, when the precision required is very high, then I use a calculator, or when the numbers involved. So, it is up to 4th decimal, 6th decimal that we have to measure or we have to calculate, and then we need the help of a calculator, otherwise we do not need a calculator. If you have a simple quadratic equation where you can factorize the terms and get the roots directly, you do not need a computer to calculate that. But if the quadratic equation is complicated, where you cannot get analytical solutions, then you have to use a computer to solve it. So, exactly like that, practical effects, phenomena and applications which can be dealt with ray optics or wave optics, we do not need to go to quantum optics, but there are applications, as I mentioned, for example, the detection of gravitation waves. I just mentioned detection of gravitation waves. The variation in the optical power levels to be detected is extremely small and extremely precise, and one has to go for quantum optical techniques to detect these gravitational waves. So, the approach, why do we need different approaches? We use different approaches either when one of the approach is not applicable, as I will show subsequently, then we have to go for another approach which is more advanced, which takes care of the limitations, or when the precision required is so high that one of the approaches or other approaches fail, then we have to go for, just as the example of a calculator, need of a calculator or a need of a computer to take care or to calculate difficult calculations which are with high accuracy, which we cannot do by our mental calculation or simple analytical solutions, then we go for calculators. Exactly like that, when the approach is necessary, when the other approaches fail, then we go to quantum optics approach. And today quantum optics is extremely important with novel applications coming out. All right. With this, I will proceed to recall some of the facts which already we know. So, recall that light is an electromagnetic radiation. Very quickly we will recall, most of these are familiar to you at your level, and the visible light corresponds to a small spectrum, a small portion of the spectrum of electromagnetic radiation. So, what I have shown here is on the x axis the wavelength and different regions of the wavelength. So, visible light is here between 400 nanometer for wavelengths corresponding to 400 nanometer to 750 nanometer is the visible region. Below this we have the ultraviolet region, and of course, if we go down further we go to the X-ray region and gamma ray region with wavelengths which are of the order of angstroms. On the other hand, if we go to the other side here, that is longer wavelength region, we go to infrared and then millimeter waves, microwaves and so on. So, electromagnetic radiation has a wide spectrum, that is the range of wavelengths, out of which visible light occupies a small band between 400 nanometer to 750 nanometer. This is the first. Second, we normally say that white light comprises of 7 colors, but there are no discrete 7 colors. So, it is actually a band of wavelengths with continuously varying shades from this end to that end, continuously varying colors and shades from the violet end to the red end. However, so just to identify a certain range of wavelengths, we could call the wavelength from approximately 390 nanometer to 420 nanometers as violet region, indigo region from 420 to 450, 450 to 500 as the blue region, 500 to 550 as the green region, 550 to 600 as yellow, 600 to 650 as orange and 650 to 750 as red. I must emphasize that these are not hard boundaries, these are just approximate boundaries to mark the commonly called 7 colors, which is denoted as VIBGYOR: violet, indigo, blue, green, yellow, orange and red. Why is it important? Because if someone says I have given you blue light, then I know that we are talking of wavelengths around 450 to 500 nanometers. If it is yellow light, we know that we are talking of approximately 550 to 600 nanometer region. The very well known sodium lamp, the sodium lines D1, D2 lines have a wavelength of about 583 nanometers. So, that is the yellow line of sodium. So, we know that it is the approximate range of wavelength corresponding to this. That is why this range has been marked, otherwise these are not hard and fast boundaries. Second, the common light sources, some of the common light sources, the tungsten bulb, the bulb which we have where a tungsten filament burns, these are broad spectrum, broad wavelength range. In fact, this tungsten bulb gives you wavelengths from anywhere from 200 nanometer, an incandescent bulb gives to 200 nanometer to 2000 nanometer, that is from UV to right up to infrared 2000 nanometer, it is a broadband spectrum. The fluorescent tube again a broadband light source which looks white. LED bulbs, the LED bulbs used for domestic lighting, they are again broadband sources which looks white, and the LEDs which are used in instruments and various panels which may be red, yellow, blue, different colored LEDs may have wavelengths. As you can see, the red wavelengths is around 650, yellow is around this, and blue is around 420 nanometer. The laser, the orange red laser, the common laser which is the Heine laser, widely used Heine laser, which I am sure most of you have seen, the common Heine laser which is here. So, here is the Heine laser. So, it is the orange red color, and that is 633 nanometer. In fact, it is a precise wavelength, 632.8 nanometers is the wavelength of this laser. The green laser, which is also used widely in various applications, pointers for example, with the brighter outputs. So, let me show the here. So, this is at 532 nanometer, it is a laser at 532 nanometer. So, the lasers are highly monochromatic sources of radiation, and therefore, so 532. Similarly, you have blue lasers with the different range of colors about 430 to 450 nanometers. So, these are some of the common light sources. The second point is the speed of light in vacuum C0 is 3 into 10 to the power of 8 meters per second, meter second inverse. Of course, the precise value of C0 is about 2.99792458 into 10 to the power of 8 meter second inverse. So, it is written up to so many decimals not because some calculator gave this value. Today, it is possible to measure precisely the velocity of light with this kind of precisions, accurate to as many decimals. It is possible to measure, and that is why the precise value of C0 is given here. In a material medium, light travels at a slower speed, which is given by C is equal to C0 by n, where n is the refractive index of the medium. Therefore, n is equal to C0 by C, which is greater than 1. We know that n, for example, typically glass has refractive index of 1.5, water refractive index 1.33. So, the refractive index is normally greater than 1 for practical media, and therefore, the velocity of light in a medium, the speed of light in a medium is slower, is lower compared to the speed of light in vacuum. So, speed of light in vacuum is the highest speed, which is 3 into 10 to the power of 8 meters per second. Third, the speed of light in any material medium depends on the wavelength. So, some of these aspects we will discuss in detail in the subsequent lectures. So, C is equal to, is identically equal to C of lambda, which means velocity of light is a function of the wavelength. This implies n is equal to C0 by C of lambda. So, just now we had written n is equal to C0 by C. So, here, so n is equal to C0 by C. Now, I am saying in the medium C is a function of lambda, and therefore, this implies that n is a function of lambda, that is refractive index is a function of lambda. The basic reason of this, one has to go to the microscopic picture, because then we can see that refractive index basically represents the response of the medium to the incoming electromagnetic radiation. The response of the medium is a function of the wavelength, and therefore, the refractive index is a function of the wavelength. So, this detail is not part of our level, and therefore, part of this course, and therefore, I would not go into further details of this, but we assume or we should note that n is a function of wavelength. Refractive index of an optical medium depends on the wavelength of light. This leads to an important phenomena called dispersion. This we will discuss in detail, phenomena called dispersion, where light of different wavelengths disperse in different directions. So, in this course, therefore, let me come to now specifically the coverage that we will have in this course module. So, in this course we will discuss two approaches, namely ray optics approach and wave optics approach in dealing with light. So, in ray optics, three important phenomena, which is reflection of light, we will discuss in detail: reflection of light, refraction of light, and dispersion of light using the ray optics approach. Using the wave optics approach, we will discuss again three important aspects, namely interference of light, diffraction of light, and polarization of light. I must mention here that reflection, refraction, and dispersion can be described using wave optics approach as well, but the reverse is not true, that is interference, diffraction, and polarization are concepts from wave optics. These cannot be explained by ray optics. So, wherever ray optics is applicable, it is simple, and we follow ray optics to discuss these three, but these three phenomena or these three important aspects will be discussed using wave optics. So, this also illustrates where, with this we will also illustrate that where one approach is applicable over the other approach. In some cases, a particular approach is not applicable, or one has to follow another approach to discuss the observed practical phenomena and to deal with the applications. At this level of discussion, we need a textbook as a backup and a reference. So, in this course module, I will follow the textbook, which is the physics, a textbook for class 12 by NCERT, New Delhi. So, NCERT standing for National Council of Educational Research and Training. So, we will follow this textbook. This has large number of worked out examples and large number of exercises, and I would try to stick to the notation of this book. There are as far as possible, and we will try to follow this book, and those of you who follow, you can have this as a backup. However, I must say that there are large number of very good books, extremely good books, and I just want to list a few of them, just list a few of them. Some of the reference books: Fundamentals of Physics by Halliday, Resnick and Walker, a very standard book. This is by John Wiley. There are several editions. Similarly, Physics for Scientists and Engineers with Modern Physics by Survey and Beischner. Concepts of Physics by H.C. Verma, a colleague and professor at IIT Kanpur, a very widely used book. This has 2 volumes, volume 1 and 2, Concepts of Physics. And for optics, specifically for optics, you could also follow this book by Professor Ajoy Ghatak, who was a former professor at IIT Delhi. I must again emphasize that there are large number of books, very good books which are available, but it is more important that one should stick to 1 or 2 books and try to work out the examples and exercises given in these books rather than trying to follow large number of books. Before we proceed with our formal lectures on formal topics, so let me just discuss about some optical components. I would show some of the optical components for those who have not seen these components. So, first a double convex lens. So, let me I have just picked up some components which I have got. I could lay hands quickly. So, I just picked up some components. So, let me show you these components. So, first a biconvex lens. So, here is a biconvex lens. So, let me take out the biconvex lens. I have one more biconvex lens. So, 2 biconvex lenses. So, let me show you these biconvex. So, it is a biconvex lens, which means if you see from the top, it will look like a circle. So, that is why front view or the top view is front view is like this, but if I hold it like this. So, this is the top view if you are seeing from above. So, you can see the bulge here and the bulge here. So, that is why when we show like this, what we are showing is the side view either from this side or from the top. So, when we show a lens, a biconvex lens like this, then we are looking at this from the top. So, we can see the bulge here and the bulge here. Both the surfaces, this surface here, this is the surface, upper surface, and this is the lower surface. So, both form parts of sphere. They may be of the same radius here, the sphere of radius r1 and r2 with a center C1 and C2. So, the radius may be same or they may be different, but this is when a convex lens. I hope you can see these surfaces here. So, this is one surface and this is the second surface. We can also see this clearly here, that if I, so you see the magnified image of the grid. So, you can see the magnified image of the grid through the lens, or if I place on any one of these. So, we can see that as I change the size of the letters look bigger. If I another lens here, so I have another of different size. There are different applications require lenses of different size, and this is also a biconvex lens. So, you can see the bulge on this side here and on the other side here. So, this is also a biconvex lens. This is for those who have not seen. There are a large number of different types of lenses. So, we have a double convex lens, we can have a double convex lens, a plano convex lens. So, different types of lenses are possible, where both the surfaces are concave. So, this is a double concave lens. Again, each of these surfaces form part of the sphere of radius r1 and r2. r1 may be equal to r2. There are others where one surface is plane and one surface is convex. One surface is plane and one surface is convex, or a combination of these lenses. So, it is possible to have combination of these lenses. So, why do we need such kind of different lenses? We will see that depending on the application, one may have to use one or more number of lenses, and therefore, you need different types of lenses for different applications. I then come to another optical component, that is optical mirrors. Well, this is what we will start from the next class, optical mirrors, and we can see that there are plane mirrors, convex mirrors and concave mirrors. So, the shaded region here tells that this is the opaque side, the reflecting side is on the other side. The back side here is coated with the reflection coating, and therefore, this is opaque, but the front side is reflecting. So, the shaded region marks the opaque side and the front side shows reflection. And finally, I will show prisms. So, these are prisms. So, let me show just one prism here. So, this is a prism. So, we could see it like this. So, there is one surface here, two surfaces, these are the refracting surfaces and the third surface. There are three refracting surfaces and the ends are ground surfaces, which is called the base of the prism. So, whenever we keep, for example, let me keep on this. So, when we show a prism here and rays passing through this, what we are actually showing is a prism sitting like this, a ray entering from this refracting surface and emanating from this refracting surface, coming out from here. So, we are showing a cross section of the actual figure. There are of course different types of prisms, retro reflecting prisms. So, prisms which are reflecting. So, you can see this is the ground surface and we have reflecting prisms here, and we will discuss more about these as we proceed with the course of lectures. So, finally, I would like to list some practical applications of these optical components. Looking mirrors, the mirror, the plane mirror that we see, magnifying glass, the lens that I had shown itself is a magnifying glass. You can see this acts as a magnifying glass. Rear view mirrors in cars, one uses convex mirrors. Spectacles, all of us are familiar with spectacles which use both convex and concave mirrors. Cameras have large number of lenses, the bigger ones, the SLRs and the bigger cameras, but today of course almost every mobile has a camera, a small lens there which gives us very good pictures, and microscopes, telescopes, periscopes, a number of instruments. I would show microscope and telescope in one of the subsequent lectures, and we will discuss about microscope and telescope in more detail. We will also discuss the magnifying effects and magnifying power of a lens in subsequent lectures. So, with this introduction, I will stop here this first lecture on in the optics module, and from the next class we will start with the first topic, that is reflection of light. Thank you.